um, the gamma ray bursts were seen in great abundance by the Compton Gamma Ray Observatory, which was flown by NASA um, in a satellite around, going around the Earth in the 1990s. It discovered a very large number of them, nearly 3,000 gamma ray bursts, which were displayed, which was discovered all over the sky. And the picture that you have here from the from a particular instrument on board the Compton Gamma Ray Observatory, or the burst and transient burst and transient experiments shows that these objects are distributed almost isotropically all over the sky, and this ruled out that the gamma ray bursts would be taking place from among galactic objects, because the galaxy itself is a very flat spiral object, which when looked at from inside the galaxy would not be showing completely isotropic burst distribution that is seen in the Compton Gamma Ray Observatory data. Next slide. And that also actually pointed to the fact that these gamma ray bursts must be cosmologically acknowledged. That the gamma ray bursts were cosmological in origin was first discussed in print by Melvin Ruderman, to whom I have referred to in one of the previous slides. It implied that there is an enormous energy budget required if GRBs are truly of extragalactic origin, because the number of photons that you detected, the energetic photons that you detected by the Compton Gamma Ray Observatory, they have to come from very large extragalactic objects. That would imply that there is a very large, enormous energy budget that have to be filled in by the GRBs. And initially it was thought that it was perhaps even more orders of magnitude more energetic than supernovae. But this realization that some of much of the emitting plasma is actually moving out at relativistic speeds reduce the energy requirements somewhat, and people then were reconciled to the view that cosmological GRBs can in fact be produced by rather energetic end of the supernovae spectrum, rather energetic end of the supernovae in terms of their energy budgets. Next slide. So here is a figure from the Annual Reviews article I have referred to a few slides ago. This describes the number of GRBs which are as a function of their duration, and you can see that there is overall distribution of GRBs which were discovered by the SWIFT satellite, which is a more recent satellite, basically geared primarily to search and find gamma ray bursts and know their characteristics. And you could see that there is a clear separation of long duration bursts from the rather short duration bursts, which are 10 to the power minus 1 second or below. And these supernovae, these objects are not really connected with core collapse supernovae, but rather they are connected with merger of two neutron stars. But it is these long duration objects which are um, which are um, which are associated with supernovae. And on the second figure in this slide, it shows the redshift distribution of the GRBs which were discovered by the Swift spacecraft, and you could see that many of the GRBs are actually taking place in very high redshift galaxies. That means they are definitely at cosmological distances from us. Next slide. And here is a picture. Here is a three-dimensional view on the left-hand side, depicting how the radio emission from the afterglow following the GRB would evolve in both in time and frequency domain. As time goes on, the afterglow becomes fainter, but as time goes on, the afterglow also peaks at successively lower and lower frequency, radio frequency. So these are characteristics which GRB afterglow show, and people have to keep in mind these characteristics when they want to observe and get information out of specific GRBs. Next slide. The